Let's throw an examples for finite difference method using second order ODE. Okay, so we will use FD, which is represented by finite difference method to solve second order ODE with BVP. Okay, and we will show how you can translate the second order ODE into the linear algebra equations using finite difference approximation. Okay, using central finite difference method. Okay, so our second order ODE is written as y double prime equals to the Folsom function plus px y prime plus qxy. Okay, and the notation is Ri will be equals to Rxxi. Okay, Pi will be equals to P at xi. Qi will be equals to Q at xi. So those are the Folsom function, the coefficients as function of xi at basically the point of xi. Okay, and y double prime by I double prime will be equals to using central difference, right? Central difference. Using central difference instead of backward ruler or forward ruler because the central difference is more accurate. So yi double prime will be equals to yi minus 1 minus 2yi plus yi plus 1 divided by h squared, where the h is basically the step size between uxi and xi plus 1, right? So this is U equation 1, which is equals to Ri plus Pi y prime plus Qi y, right? That is the y at xi double prime equals to these equations based on the descriptions of second order ODE. Then yi prime will be equals to using central difference, which is yi plus 1 minus yi minus 1 divided by 2h, right? Then you can rewrite this equation 1. So rewrite equation 1 using the expressions of y prime represented by the central difference. So yi double prime will be equals to Ri plus Pi times yi prime, which is yi plus 1 minus yi minus 1 divided by 2h plus Qi yi. Then this is become equation 2, where you write yi double prime into algebra equations, right? There is no differentials anymore. There is no derivatives. And you are trying to find what is your coefficients, trying to find coefficients for yi minus 1, yi plus 1. And in that case, we can write as a state space representation after you find the coefficients. So yi double prime will be equals to yi minus 1 minus 2yi plus yi plus 1 divided by h squared, right? And that is also equals to this term, Ri plus Pi yi plus 1 minus yi minus 1 divided by 2h plus Qi yi. So this is based on equation 1 and equation 2. You can write yi double prime equals to this form, which is the second order central difference represent to the y double prime, which is also equals to the second order ODE using the central difference representation. Okay? And you can put all the yi coefficients, all the yi minus 1 coefficients, and all the yi plus 1 coefficients into the same term. So we get 1 plus h over 2 pi yi minus 1 minus 2 plus h squared qi yi plus 1 minus h over 2 pi yi plus 1 equals to ri h squared. So you put all the coefficients for yi minus 1, yi, and yi plus 1, and the Folsom function into the same term. And you can also write this as ai yi minus 1 plus bi yi plus ci yi plus 1 equals to Folsom function ri times h squared, right? Where the ai will be this 1 plus h over 2 pi, bi will be negative 2 plus h squared qi, the ci will be 1 minus h over 2 pi, right? And this I will be equals to 1, 2, until n minus 1 for the n minus 1 equations, which represent the inner points. Because the boundary points we will treat differently. So right now we are only solving the inner points, where the ai equals 1 plus h over 2 pi, bi equals negative 2 plus h squared qi, ci equals to 1 minus h over 2 pi. Okay? So you just get what is the coefficient for these three terms. Then what's the next? What's the next? The next, we will treat our boundary conditions. Because we say in the finite difference method, the boundary conditions will treat differently. So the boundary conditions, okay? The boundary conditions for this exam, we will treat the boundary conditions. We will first write the inner, we will first write the inner matrices first, then we will treat the boundary conditions, okay? So for the y1, y2, until yn minus 1, these are the unknown parameters. And when I equals to 1, that means our inner algebra equations will be a1 y0 plus b1 y1 plus c1 y2 equals to h squared r1, right? And if you know, okay, if you know u y0, for example, if your boundary conditions has y0, then we can say b1 y1 plus c1 y2 equals h squared r1 minus a1 y0, okay? If you have the boundary conditions. Then I equals 2, that leads to a2 y1 plus b2 y2 plus c2 y3 equals to h squared r2, okay? Then you will go to the final, which is I equals to n minus 1. That will be a n minus 1 y n minus 2 plus b n minus 1 y n minus 1 plus c n minus 1 y n. That is equals to h squared r n minus 1, okay? And if your boundary condition has yn, for example, you have the direct boundary condition, you have y0 and you have yn, then the final equation, that balance algebra equation, become bn minus 1 yn minus 1, an minus 1 yn minus 2 plus, that is equals to h squared r n minus 1 minus c n minus 1 yn, because you know what is the yn, okay? Then you can write the finite difference, those algebra equations, into a matrices format, which we also call it state space representation, okay? Representation. You can write as ay equals to b, okay? And let's assume You know the boundary condition y0 and yn. So you know the initial value and the final values. Then you can write this A is represent your coefficient matrices. This Y will be the values you don't know. So for those node values you don't know, and where is the node value is from y1, y2, y3 until yn minus 1, because you know y0 and yn. So you don't know in between y1 to yn minus 1. And that is equals to the B part. The B part is something related to your forcing function, right? So let's see what is our first equations into our I equals to 1. So I equals 1, you have B1y1 plus C1y2 equals to these forcing functions. And so the coefficient for the y1 will be B1. The coefficient for the y2 will be C1. Okay? And all the other coefficients for the other unknown node will be 0. So will be 0, 0, dot, 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 0, 0. Then what's that equals to? Equals to h squared r1 minus a1 by 0. You know by 0, so you know what is this function. Okay? Then the second line will be a2y1, b2y2, c2y3. The sum equals to h squared r2, right? So the coefficient for y1 will be a2, y2 coefficient b2, y3 coefficient c2, and all the other unknown coefficient will be 0. So 0, 0, 0. Then that is equals to h squared r2, h squared r2. Okay. Then the y3 will be, for example, a3. So it will be a3y2. Okay. We can write I equals to 3. That will be a3y2 plus b3y3 plus c3y4 equals to h squared r3. Okay. So it will be 0, a3, b3, c3, 0, dot, 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 0, 0. And that will be h squared r3. Okay. Then you can write, you know, this matrices. It's like a diagonal, but you know the diagonal matrices will be b1 until bn minus 1. Then there is a upper level and the lower level diagonal elements. So a2, a3, a4, etc. c1, c2, c3, c4, etc. Okay. So you will have until an minus 1. So that is the last equations, bn minus 1, right? So the last equation will be an minus 1, yn minus 2. That is the coefficients for yn minus 2. Then there is bn minus 1, yn minus 1. That is equals to h squared rn minus 1 minus cn minus 1 yn. Okay. So that is the matrices you are trying to solve. And basically how you can solve, you know what is here, right? You know h squared r1 minus a1 by 0, h squared r2, h squared r3 until h squared rn minus 2, and the final equations. You all know these equations. You also know the coefficients. Then you can solve what is from y1 to yn minus 1. Okay. And yeah, so that is how we can solve using the finite difference method. And we will use an example to show how we can solve.